So we're going to try this again. This is now like my fourth attempt at this. Apparently, the one on YouTube previous did not have any sound, so we'll try to get it right this time. So this is our first lecture in lesson 3, talking about stars, galaxies, and the universe. So we'll start today by talking about stars. You've seen them in the sky at night. We know that our sun is one, but what is our technical definition of a star? A star is a large sphere of hydrogen gas that is hot enough for nuclear reactions to occur at its core. So we think about the area outside of our solar system, outside, in between our solar system and the next, as being empty space. There's nothing really there, but that's not the case. There is actually quite a bit of material there, and we call this the interstellar medium. So in this area between stars, between solar systems, we have ours has the Oort cloud. So that's one interstellar object. You have um, you have gaseous elements like gaseous hydrogen. You have dust particles. You have all kinds of things in this interstellar medium. So it's not empty space. There really is a lot of stuff there. And we really have big distances to cover here. You see, going from light hours into light years. You can have things like rogue planets out there. So sometimes in this interstellar medium, you're going to get a concentration of things, a concentration of this interstellar medium. And this is what we call a nebula. So sometimes it forms a cloud. And these clouds can be huge, huge distances. They can be 100 light years across. So what's a light year? Well, a light year is the distance that light travels in a year. Now, we know that light travels at 300,000 kilometers per second. So let's multiply that out. Let's multiply that by 60 seconds in an hour, or in a minute. And then let's multiply that by 60 minutes in an hour. And then let's multiply that by 24 hours in a day. And then multiply that again by 365 days in a year. And we get 9.46 trillion. That's how many kilometers are in a light year. So we've got this massive distance, but a very concentrated area that we call a nebula. This cloud has all of these things in it, all of this dust and gas and all of this interstellar medium kind of concentrated into one area. And it's about 70% gaseous hydrogen. And so sometimes there's a kick. There can be a supernova nearby, there can be galaxies colliding, and there can be that galactic tide that we talked about. There can be a black hole giving off X-rays, just all kinds of things that can happen, and it will hit this nebula and cause it to start to have some angular momentum, start to spin. And so as it spins, we know what happens when it spins. It starts to flatten, and you get what's called a gravitational collapse. So this cloud starts to flatten, and then you get a condensation in the middle, and that's gravity collapsing and pulling things towards the middle, concentrating things in the middle, and that's where we get what's called a protostar. So as you have this gravitational collapse, you have this angular momentum. Sometimes these protostars will form, and see here is a very large nebula and some protostars kind of forming here. And the protostar, it's not a full star yet. It's still feeding on the material in the nebula there, but it will start to glow, start to have what's called an outburst. And sometimes they will start to have these flares of ionic gas coming from out of we would think of it as the top and bottom, and these flares kind of come out, and they're visible depending on what we're looking at. But so you see it's spinning around. You have these protostars forming. You have a protoplanetary disk forming, and everything's kind of spinning around, whirling about. And so as it concentrates in the center, the pressure starts to build. You have gravity pulling everything in tighter. It's becoming more and more dense, and the gases start to have more and more pressure. And we know, which we've talked about, there is a relationship between pressure and temperature. So as the pressure goes up, the temperature also goes up. And within this protostar, which again, mostly gaseous hydrogen, as the temperature and pressure start to build, there's more energy for these gas molecules. And so you have hydrogen, which is H2 in its elemental form, separating the atoms of H2. So now they're just becoming single hydrogen atoms. And these hydrogen atoms begin to connect with a neutron. So as it connects with this neutron, it becomes an isotope. And if you remember, an element can change the number of neutrons and it can change the number of electrons, but it can't change the number of protons. So this isotope is still hydrogen, but it's heavier because it now has this neutron attached to it, and it's called deuterium. It's the deuterium isotope. But then you have some of them that have 2 neutrons connected to it. That's called the tritium isotope. Now, as the pressure and the temperature increase, these particles, these atoms are bouncing around. They're getting all kinds of extra energy, and sometimes they will collide just right, and we get fusion. So in this fusion reaction, there is a huge release of energy, tons and tons of energy. But then these 2 atoms are going to combine, and so now we have an atom that has 2 protons and 2 neutrons. So it's no longer hydrogen, but it's helium. And then it kicks out that extra neutron. So you have this release of energy shaking up the atoms within that cloud. You have this extra neutron now bouncing around. And so it will combine with another hydrogen atom, proton, in order to form another deuterium. Or it could, 2 of them could combine to form another tritium. And as the energy forces them around, those 2 can combine. And again, we have more reactions. So it's a chain reaction. So what's happening as the temperature and the pressure increase, you have nuclear reactions happening in this protostar. Now, we've mentioned the different phases of matter. We've talked about solid, liquid, and gas. So as you add energy to a solid, the particles start to free up from each other and become more free-flowing, and it becomes a liquid. Then you add more energy, and that liquid, in that liquid, the particles start to get more energy, and they free up, and they break away, and it becomes a gas. So what happens when you take gas molecules and you continue to add pressure and you continue to raise the temperature, they get more energy and more energy. Well, what happens is the atoms, the electrons in those atoms start to break away and they become a little more free flowing. And so then now that gas is ionized and it is able to conduct electricity. But think of this on a large scale. And that's where we get the 4th phase of matter, plasma. So gas particles have tremendous heat or tremendous pressure, and the electrons break away, and it starts to be conductive. It starts to conduct electricity, and that's what's plasma. So when we have a star, a protostar, that has these chain reactions, these nuclear reactions, where hydrogen forms into helium, or sometimes heavier elements combine and help change hydrogen into helium, and creates plasma, that's when we have what's called a main sequence star. In that main sequence star, you have these nuclear reactions, and then the force of gravity pulling things in is equal to the force of pressure pushing out. And if that sounds familiar, that's what we call hydrostatic equilibrium. Remember we said when things have a nearly round shape, it's called hydrostatic equilibrium. Well, what the definition of that is the force of gravity pulling in is equal to the force of pressure pushing out. And so now it's not feeding off of the gas around it. That continues to swirl around and makes maybe planets or asteroids or whatever else. But this star is now feeding off of the hydrogen inside of it, creating plasma, and it's on its own now. It's a main sequence star. Now this is our sun, and our sun is in that main sequence phase of a star. Now we'll talk a little bit more about the evolution of a star, the life cycle of a star, later. But for now, this is the formation of a star, and this is the reactions that power a star.